Hi, everyone. My name is Adam Chapman, and I'm the sales manager here at Westermeyer Industries. I want to thank NASRC for putting on this year's Sustainable Refrigeration Summit and for the opportunity to be a panelist today to discuss what Westermeyer Industries has to offer to the natural refrigeration sector. Here at Westermeyer Industries, we design and produce pressure vessels and supplementary devices for the refrigeration and air conditioning industry. We pride ourselves on being a problem-solving company. We identify needs and develop solutions that will continue to improve the design and functionality of the systems on which our products are used. The primary style of oil separator used for transcritical CO2 applications is the coalescing oil separator. But what is an oil separator's purpose? The coalescing method utilizes a borosilicate glass fiber filter, which flows from the inside of the filter to the outside. The oil-laden refrigerant vapor travels into and through the filter, allowing small oil particles, almost aerosol form, to encounter the glass fibers. As an oil encounters these fibers while traveling through the filter thickness, they coalesce or become larger and larger. Once the vapor and oil reach the outside layer of the filter, the oil is now in full liquid form, and gravity allows the oil to drain downward and away from the filter, thus allowing the oil-free refrigerant to exit the oil separator, free of any untrained oil. When sized correctly, coalescing oil separators will remove up to 99.5% of any entrained oil from the refrigerant. At any point that the filter needs to be changed, it can be serviced through the top flange. The heart of our coalescing oil separators is the filter element itself. Our filter construction is paramount to the effectiveness and longevity of our products. We have both an inner and outer expanded metal wrap to ensure the fiberglass media is protected from large system debris. And in contrast to other filters in the market, our separating media also includes an additional drain layer for optimal separating performance. Lastly, our new press-fit gasket assists with compatibility without the need of adhesives, while also providing excellent reinforcement against spikes and mass flow. Because our gasket wraps on the inside of the filter cap, this provides a high surface area for sealing. So, when do you need to replace the filter? Over time, coalescing filters get contaminated with system particulates and therefore need to be changed. If the filter becomes obstructed, either your gasket will blow out, resulting in oil level alarms, or worse, the filter can rupture. A catastrophic failure like this can be quite costly. On average, an on-site tech call will take anywhere from 5 to 6 hours. At an average of $110 per hour, that equates to approximately $550 to $650. If this occurs after hours, you're looking at a charge between $575 to $1,000 plus, depending on how contaminated your system has become. Filter contamination results in a reduction in flow through the separator, which can be measured as a pressure differential, or otherwise known as a pressure drop. You may also hear the term delta P used in the industry. We recommend that the filter is changed immediately when the differential exceeds 12 psi. Not only will measuring the differential across your filter assist with preventing a catastrophic failure, but it also can assist with energy consumption. On average, refrigeration systems, if a 12 to 15 psi pressure drop is experienced, that is going to equate to approximately 4 to 5% increase in energy consumption. So this is a balance. You need to ensure that you are monitoring the pressure drop to keep your energy costs down and to prevent a catastrophic failure. But if you don't know when to service your oil separator, you may be changing the filter too often, which will increase your service costs. A differential monitor should be used to measure pressure drop across the oil separator. Therefore, we're proud to introduce our new RDP01T pressure differential monitor designed for transcritical CO2 systems. This device provides LED readouts for visual indication, an analog output that can be tied back to your rack controller, highly accurate pressure transducers that include a 6-foot cable, and this device is factory calibrated using our patent pending processes, which is provided in a weather and dust resistant case. So, where's this device located? You install the transducers just between the inlet and outlet of the oil separator so you can properly measure the pressure drop across the filter element itself. Please be mindful that an access valve is going to assist in servicing of this device in the event it needs to be replaced. Not only is this product capable of providing a single differential output voltage from 2 independent pressure transducers, which ultimately saves time for installing in the field, but by plotting your output readings on your system controller, this gives you the ability to provide preventative maintenance measures for your service technicians. So the big question is, what benefit does this product have compared to 2 individual transducers that I can buy separately? The answer is calibration and accuracy. And our solution is that we have developed a proprietary calibration process to ensure accuracy and ease of use. The graphs shown here are developed on a real-life test stand in our lab and illustrates the benefits of our patent-pending calibration process. So, what was the process? We took uncalibrated transducers and exposed them to measurable pressure drop, which is illustrated in the blue bars. We took those readings and received an output, which is referenced in the orange bars. We then took the same readings and rerouted those outputs into our calibrated device, which is referenced in the green bars. Those experiments were replicated across 4 different inlet pressures shown at the top of each bar chart. As you can see, the green bars are much closer to the reference pressure differential. What this tells us is that through our calibration process at multiple oil separator inlet pressures, we are able to reduce the error band that out-of-the-box transducers provide. Now, I'm sure you all observed on the previous graphs where the inlet pressure that they're lower than what we would anticipate for transcritical CO2 applications. This graph presented here is a variation of the bar chart presented in the previous slide and is meant to illustrate that the results are not dependent on the separator inlet pressure. The results are plotted here as the average value of the difference between the pressure differential and the reference pressure differential versus the reference pressure differential itself. The error bars correspond to plus or minus 1 standard deviation. The calibrated pressure transducer results are in orange, while the calibrated pressure transducers are in green. Ideally, our experiment results would be as close as possible to coincide with the x-axis, as that would mean that they would follow the reference pressure differential closely. However, it is also clear that this graph, there's a big deviation between the uncalibrated results and the calibrated readings across the whole differential range, with the calibrated readings being far more accurate. In addition, by observing the average values and their corresponding error bars for the 2 different cases, uncalibrated versus calibrated, it is clear that the results are statistically significant, given that we're looking at 2 very distinct data clusters. But that is not the case when we're looking at each data individually, where multiple separator inlet pressures are utilized. This all means that the results are not dependent on separator inlet pressures, and the accuracy trends shown in both graphs presented so far are expected to remain the same outside the range of separator inlet pressures explored in our experiments. So here are a few key features that I'd like to note. This product requires a power supply of 10 to 24 volts AC or DC. It provides an analog output of 0.5 to 4.5 volts, which is a range of 0 to 20 psid. There's also, as I indicated, a visual indication on the front with multicolored LEDs. Operating temperature for the electronic enclosure is at -40 to 175 degrees Fahrenheit. The pressure transducers can operate between -40 and +275 degrees Fahrenheit. And they come with a 6-foot cable and an 1/8" male NPT thread. The maximum operating pressure is 2000 psig, and the overpressure protection rating is 4000 psig. So, what value does this bring to the industry? This device assists in maintaining system efficiency through the oil separator. It allows for differential readings that will both help with minimizing pressure drop, as well as preventative maintenance measures to keep from having a catastrophic filter failure, which all translates to saving time and money. We anticipate having this product fully launched by Q4 of 2021. Currently, we have several units in the field that are providing very positive results, but we do have some devices available for field testing, so please contact us for more information if you are interested. I want to thank the team at NASRC for the opportunity to present this product to the industry today. Please do not hesitate to reach out to us for more information on this product. I've listed my contact information alongside my colleague, John Gallagher. I want to thank you all for your time today. Take care and be safe.